Excuse me, sir.
Yeah,
Sir, I have a question, sir.
yeah, tell me please.
Sir, if we are meshing two triangular elements of dissimilar size,
Okay.
sir, will there be an issue in inter-element compatibility along the common edge?
No, they can be of any size, no, because if it is a triangular element, the displacements are linear in x and y, so you will still have a linear variation along that line as long as that line is common. So the end nodes have to be common between the two elements, but
Sir.
their sizes could be different.
Yes, sir. Yes, sir. Thank you, sir.
Okay.
Same, sir.
Yeah.
Sir, in the first question of the assignment 3, in that question we have to take insulated edges, or we have to take that heat is
Yeah,
being
you take
transferred to the
insulated. Yeah, take insulated edges. I actually didn't ask you to solve. Only I think you have to set up the assembled equations, right? So yeah, you take the other edges where nothing is given as insulated edges. Yes.
And sir, in eighth question, sir, a nomenclature of figure has not been carried out, sir. You have asked to us to define HAB, across HAB, but we are not aware which edge is AB.
Okay, and let me. So I have said no, an assembly of three noded triangular elements and four noded rectangular element is shown. Sketch the shape or inspiration along obtained from elements 1 and 3 and is okay. So yeah, so AB is the edge common between the quadratic element, no, this quadrilateral element and the triangular element. So you take the element to one, basically this bottom triangular element, two as the top triangular element, and three as the this quadrilateral element, and then the AB is a common edge between triangle and quadrilateral.
Yes, sir.
Yeah. Any other question? Okay, then let me start. So we are discussing the plate bending elements. So what I think I had discussed this displacement approximation. So we are going to restart from there. So we said displacements based on first order shear deformation theory. So this I had said. So the displacement u, which is in general a function of x, y, and z, is written as u naught, which is a function of x and y, plus z into theta y, where theta y is the rotation about positive y axis, and of course u naught and theta y are functions of x and y. So essentially we are assuming that the displacement along x direction varies as a linear function of z. And similarly we said v also in general a function of xyz is written as v naught, where v u naught and v naught are the displacements of the any point on the middle surface of the plate, and minus z into theta x, where theta x is a rotation about positive x-axis. I had also mentioned that in the literature you see that sometimes this u is written as u naught plus z into theta x, and v is written as v naught plus z into theta y. So then actually theta x in that nomenclature is the rotation about y-axis, and theta y is the rotation about negative x-axis. But since now in the softwares we have degrees of freedom as the displacements along xyz and the rotations about xy and z axes, so that is why I have kept this formulation in this manner. And w is assumed to be function of only x and y. So we assume that all along thickness direction w does not vary. Basically that is how we are taking this approximation. And I had mentioned that what are the assumptions. I know the main assumption in this is that straight line normal to the middle surface remains straight to the middle surface after deformation, but not necessarily normal. So basically transverse shear strains are non-zero in this case. So once we look at the displacements, so you would see that the steps are same. So now when we look at the strains, so the non-zero components of strains in this case are going to be, so if I look at the epsilon, so the using the work notation we are writing the strain as a vector. So epsilon is basically having normal strain along x, so epsilon xx, epsilon yy normal strain along y, and then the shear strain gamma xy and gamma xz transverse shear strains and gamma yz. So these are the non-zero. So there are 5 strains, independent strains, 2 normal strains along x and y, and 3 shear strains gamma xy. Gamma xy is in plane shear strain, and gamma xz and gamma yz are transverse shear strains. So I know by definition now we know that epsilon xx, the normal strain along x direction is basically change. I know if you take a line element parallel to x-axis, so change in length per unit original length in the limit when length of the line element approaches to 0 is called as normal strain along x direction. So that is del u by del x, and u no we know here u is written in terms of these two variables. So then you basically write del u by del x as del u naught by del x plus z into del theta y by del x. And similarly a normal strain along y direction is rate of change of v with respect to y, so del v by del y, and again we know that v is equal to v naught minus z into theta x, so we get this as del v naught by del y minus z into del theta x by del y. And then the in plane shear strain gamma xy is change in angle between line elements parallel to x and y, so del u by del y plus del v by del x. So now if you again use the the formula for u and v, so we get del u naught by del y plus del v naught by del x, and we get plus z, and then we have del theta y by del y and minus del theta x by del x. So no, these are the in plane strains epsilon xx, epsilon yy, and gamma xy. Then if you look at the gamma xz, so gamma xz is del u by del z plus del w by del x. So now if you put the definitions of u and w, so u is u naught plus z into theta y, so its derivative with respect to z would be simply theta y, and u is only function of course x and y, so we have plus del w by del x. So and similarly gamma yz, if you look at, that would be del v by del z plus del w by del y, and del v by del z is minus theta x, derivative of u v with respect to z would give minus theta x plus del w by del y. and these strains are known as the transverse shear strains. Transverse shear strains. And for the classical plate theory, where we assume that the normal to the middle surface remains straight and normal after deformation, so there the gamma xz and gamma yz would be zero, so you would get theta y as minus del w by del x and theta x, x as del w by del y. And accordingly, then the expressions for u and v would be only in terms of u naught, v naught, and w. So that is what you can see. So now what actually we do is no, these are all the strains, because no, we have the z coordinate separately over here. So if you look at the epsilon xx, epsilon yy, gamma xy, gamma xz, and yz, so z is separate, their variation through the thickness along the z coordinate is known. So we can rewrite this strain, all the strains, 5 strains put together. Epsilon is equal to basically a matrix involving just z coordinates, and then the strain which are only functions of x and y. So if you look at what I'm going to do is, in epsilon xx, the first epsilon yy and gamma xy, I'm going to write the terms which are independent of z. So that is, if you look at, this term is independent of z, this is no independent of z, this term is independent of z. So first I'm going to write that, and then you have these curvatures. So actually del theta y by del x, del theta x by del y, and similarly del theta y by del y minus del theta x by del x. These are the curvature terms and they are coming with the z. So I'm going to separate them out, and the transverse shear strains at the end. So I can write those. So in the epsilon xx you have del u naught by del x, then you have del v naught by del y, then we have del u naught by del y plus del v naught by del x. So these are the terms which are independent of z. Then the curvature terms which are coming with the z. So we have del theta y by del x, and we have minus del theta x by del y, and then we have del theta y by del y minus del theta x by del x. And then we have that these transverse shear strains. So we have theta y plus del w by del x, and we have theta x plus del w by del y. This is minus theta x plus del w by del y. So now if you look at epsilon, so epsilon xx is del u naught by del x plus z into del theta y by del x. So I can write here 1, and then this del theta y by del x term is coming. So I put two zeros, and then it is going with a linear, as a linear function of z. So I put that as z, and then we have these remaining 4 terms. So I put here 0 0 0. So that is epsilon xx component. Then epsilon yy is del v naught by del y plus minus z into del theta x by del y. So here 0 1, and then 0 0, and minus is already there, so I put here basically z, and then this 0 0. And then gamma xy is del u naught by del y plus del v naught by del x. So 0 0, third term is coming, and then no, the sixth term is coming, and 0 0. And then if you look at the last two transverse shear strains, gamma xz and gamma yz, so they are as it is. So this column is 1 and 0, and then you have 0 0 0 0 0 and 1. So this becomes we can separate out the epsilon variation in z and xy separately. So if you look at this epsilon, there are 5 components. It's a 5 by 1 vector, and this is 5 by 8, and this is 8 by 1. So I'm going to use a notation. So let me say that this epsilon is equal to z matrix. So this matrix I am writing as a z matrix, this whole matrix, and this strain, which is these terms of the strains, which are functions of only x and y, are in natural coordinates would be functions of xi eta. So I'm calling as epsilon bar. So this matrix is defining this epsilon bar, and as I said, this is 5 by 1, and this is 5 by 8, and epsilon bar is a vector of 8 by 1. So this is as far as the strains are concerned. So it is similar to other problems. Only thing is we have more number of strain components, and out of those epsilon xx, epsilon yy, and gamma xy are functions of basically linear functions of z coordinate. Then if you look at the stresses, so the non-zero independent component of stresses I am again putting as sigma. So there are going to be 5 independent components of stresses: sigma xx, sigma yy, sigma tau. No, the sigma zz. We are taking plane stress along the thickness direction, so it's a generalized plane stress. So we have tau xy, tau yz, and tau z. No, let me reverse this the sequence of tau yz and tau zx. So we have tau xz and tau yz. So these are the basically stress components which are non-zero. So at any point in plate bending problem, you will have 5 components of stresses: sigma xx, sigma yy, tau xy, tau xz, and tau yz. So 2 normal stresses and 3 shear stresses. Out of tau xz and tau yz are transverse shear stresses. Now we want to relate the stresses and strains. So for that, let me consider the material as linear, elastic. So linear means the relationship between stress and strain is linear, and then it is elastic. That means when we unload the material, it comes back to its original configuration, and the properties are same in all the directions. So basically it is isotropic material. And additional thing we are assuming here, that we have generalized plane stress condition. So when you say plane stress, so then basically sigma zz, tau xz, and tau yz, all three stresses involving z coordinate are 0. But in generalized plane stress, we are saying that only sigma zz is 0. So here we have generalized plane stress condition. And generalized plane stress condition, what we are saying, that sigma zz, the normal stress along the thickness direction is 0, but tau xz, these transverse shear stresses, and tau yz are not equal to 0. So under this, no, again the form of relationship between stress and strain is going to be same, the somewhat similar to what we did for the basically plane stress problem. So another, I am going to write the relationship as sigma is equal to C into epsilon. Sigma is a 5 by 1 vector, C would be a 5 by 5 matrix, and epsilon is going to be 5 by 1 vector. So of course in 3D we have seen that the C was a 6 by 6 matrix because we had all the stresses and strains non-zero and independent. But here now we have only 5 non-zero stresses. Sigma zz is 0, and only one no 5 independent strains. Epsilon zz can be written in terms of the others. So that is why we have this constitutive matrix involving 5 by 5 constitutive matrix. So where if you look at the constitutive matrix, that is C. So C is similar to what we had, no, the plane stress case. So the procedure to derive is similar. So I'm not writing the intermediate steps. So you will have, if you recall, we had E upon 1 minus nu square, and then we had the 1 nu. But now here there are 5 components. So 3 are shear, and in isotropic material there is no coupling in shear and normal. So I put there 0, and then this is nu 1, again 0 0, and then there is no coupling between the various shear components. So we get 1 minus nu by 2. Why we are doing this 1 minus nu by 2? So that when we multiply E upon 1 minus nu square into 1 minus nu by 2, we get E upon 2 into 1 plus nu, which is G. So we want to get basically G shear modulus. So that is we have similarly for the tau xz and similarly for the tau yz. So this is your constitutive matrix where E is Young's modulus and nu is Poisson's ratio, as you know. E here is Young's modulus, and nu is Poisson's ratio. So once we have an idea about the basic variables involved and the basic relationship between what is the displacement approximation, what are the strains, what are the stresses, what is the relationship between stress and strain, then we can talk of the total potential energy functional. And in the total potential energy functional, although we also use what is known as a concept of basically shear correction factor, which I had introduced in the Timosenko beam element, but I am not introducing that, but we actually use the transverse shear correction factor in the when we talk of total potential energy. So the next quantity which we need to define is the total potential energy functional. Of course, we can always derive this from the differential equations. We write the differential equation in terms of displacements and rotations, and then write the weak form. Then from there we can arrive at this integral functional. But I am writing it directly. So total potential energy functional, because we know for these structures very well defined strain energy and the potential of the forces, so we can write directly. So here, as I said, I am not considering the shear correction factor. So then the total potential energy functional I would be consisting of strain energy. So that we know is strain energy is integration over half integration over the volume sigma transpose into epsilon, and sigma is C into epsilon. So its transpose would be epsilon transpose into C transpose. So as you see here, C is a symmetric matrix, so its transpose is equal to C. So we would be able to write this as epsilon transpose into C into epsilon, and then the integration over volume minus, now we are taking, as I said, if you recall, in the last class I had said that we have only load which is the transverse load. So because the potential of transverse load is going to be q dx dy into w, and since the work done is positive, we are taking q in the direction of w, so the work done is positive, potential is negative, and then I am putting here w transpose, so that matrix vector multiplication subsequently is consistent. So we have this dx dy, and then we have the potential of boundary forces, so that involves the boundary integral. And then the boundary integral I am going to write in terms of u naught v naught w theta x and theta y. So what we are taking is that this transpose, and let us say on a boundary gamma, for there is a outward normal n, so the axial force is n x along x, and n y along y, and the shear force along the z direction is, let us say, capital Vz, and then the moment about x axis on that boundary is mnx, and the moment about y axis is mny. So see, you get, you see that u naught into nnx gives you the potential of force along x direction on the boundary having outward normal as n, and v naught into nny with a minus sign of course gives you the potential of force nny along y direction, and w into vz gives you the potential along the potential of force along z direction on the boundary, and theta x into mnx gives you the potential of moment along normal along x direction, and similarly no that is about x axis, and theta y into mny gives you the basically potential of moment about y axis on the boundary having outward normal along direction a. So this into ds. So this becomes only, these are the here if you look at basically this nnx nny. So let me define these quantities. So here nnx is the, so this is going to be force per unit length, and that length is going to be actually the length along y, so y length, so force per unit length along x direction on the boundary with outward normal n. So that normal n is normal to the boundary, and similarly n and y is similarly force per unit length. Now this would be again on the same boundary. So it could be that boundary could be of course any boundary. So along y direction, again on the boundary with outward normal n. So because boundary will have a normal, and of course for a rectangular plate the boundary normal would either be parallel to x-axis or negative x-axis, or y-axis or negative y-axis. So that is what would be n in that case. And Vz is this is force per unit length along z, and on the on the boundary, so those things are same, on the boundary with outward normal n. And then similarly mnx is the moment per unit length. So this is also per unit length, so moment per unit length about this is moment about x-axis, on the boundary. So those things are same, on the boundary with outward normal along n. And similarly here m and y is moment per unit length about y axis, again on the boundary with outward normal along n. So these are the boundary forces and their potential which is included there. And now what we actually want to do is now we have seen one more thing, that the thickness integration we want to separate it out. So if you see here we have written basically the strain epsilon as z matrix involving z coordinate, this matrix, and epsilon bar. So I want to write that and then carry out the thickness integration explicitly. So you would be able to see that the I then can be written as half, and then area integral, and then the integration along the thickness would be minus h by 2 to plus h by 2, where h is the thickness of the plate, and then epsilon is z into epsilon bar. So epsilon transpose would be epsilon bar transpose into z transpose. So I will have here epsilon bar transpose into z transpose, and then in between we have the C matrix, and then again epsilon, and epsilon is z into epsilon bar, and then of course the integration is dz, dx, and dy. And similarly of course the other terms are remaining as it is. So the integration over area of the element, we have w transpose q dx dy. So yeah, and then same thing, the boundary integral remains same. So potential of the boundary forces, so we have u naught v naught w theta x and theta y transpose, and into we have nnx nny vz mnx and mny ds. S is along the boundary. And now what we can actually do is, now out of this, because this epsilon bar is a function of only x and y, this epsilon bar is a function of x and y, so they can be taken out of the thickness integration, z integration. So, and that thickness integration I am going to define as a matrix C bar. So then you can write this integral as half, and then integration over area of the element, and then we will have epsilon transpose, and then this integration no my integration minus h by 2 to plus h by 2 z transpose into C into z dz. I am calling it as a C bar. So this will be, let us say, C bar, and then we will have, of course, now again the epsilon bar, and then we have the dx dy, and the other terms remain as it is. So no, there is no change in the other terms. So we have minus integration over area w transpose q dx dy, minus we have boundary integral, and then u naught v naught w theta x and theta y transpose, and n nx n, we have this n n y vz and m n x m n y ds. So this remains as it is. Now where, let me define what this C matrix is. So basically C matrix is minus h integration minus h by 2 to plus h by 2, and this Z matrix into C into Z is now dz, the integration with respect to z, we are calling it as a C matrix. And this, of course, if you see Z matrix, if you see, it is basically 5 by 8, and C is 5 by 5, Z transpose would be 8 by 5. So ultimately C bar matrix will be, you would see that it is going to be a matrix 8 by 8. Of course, many elements are going to be 0 in this matrix when you multiply and see, but the overall it is going to be a matrix of size 8 by 8. So yes, once we have done this, then we look at the, now we have well defined integral functional, which involves the unknowns u naught v naught w theta x and theta y, which are functions of x and y. So we will have to talk about the interpolation of these variables. So when we develop the element, so we obviously talk of the interpolation of the unknown variables. So in this case, we are having, basically, if you look at the when we look at the displacement approximations, so the primary variables in this case are going to be u naught v naught w theta x and theta y. So this should be basically degrees of freedom at the nodes of the element, particularly the boundary nodes of the element. So that means there would be 5 degrees of freedom at each node. And suppose we go for a 4 noded quadrilateral element, isoparametric element, then per element there would be 20 degrees of freedom, 5 degrees of freedom per node, and 20 degrees of freedom per element. So the that is what the kind of interpolation we would use for this element. So now let us talk of interpolation. So as I said, I'm going to use the 4 noded isoparametric element. So many concepts which we have discussed for the isopar. Now you could have, say, 4 noded isoparametric element. You could have 8 noded isoparametric element. You could have 9 noded isoparametric element, and also even it is possible to formulate a triangular element. So you can formulate a triangular element with the displacement variation along x y. U naught as linear function of x and y, v naught as linear function of x and y, w as a linear function of x and y, theta x linear function of x y, and theta y as linear function of x y. So that is also possible. So you could think of all the different kinds of elements which can be formulated for this problem, as we have defined the integral functional, and we know what are the primary variables and what is the differentiability requirement and inter-element compatibility requirement. So what I am talking about here is the 4 noded isoparametric element. So that means the element in the physical coordinate space can be any arbitrary quadrilateral. These are the local node numbers, and then this element is mapped to a natural coordinate space. So in the xi eta coordinate space, we have this xi and eta. The nodes are 1. So the node numbers 1, 2, 3, and 4 in the physical and natural coordinate have one-to-one correspondence. That means this node is corresponding to this node in the physical coordinate space. This is corresponding to this. This is corresponding to this. This is corresponding to this. And then any point inside the element is, you have some point here. There would be corresponding point xy in the physical coordinate space. So as I already said, the if when you look at the nodal degrees of freedom, so each node we have to have these primary variables basically as degrees of freedom. So nodal DOFs, degrees of freedom. Nodal DOFs means degrees of freedom. So these are u naught, v naught, w, theta x and theta y. These have to be there as the degrees of freedom at the elements. So we will have basically u naught. No, for the ith node it would be u naught I e, v naught I e, w I e. For I is the node number. It goes takes values 1, 2, 3, and 4, and then you have theta x I e and theta y I e. So these are the 5 nodal degrees of freedom. So as you see, these are 5. So per node there are 5 degrees of freedom, where u naught, v naught, and w naught are the displacement along x, y, and z, and theta x is the rotation about x axis, and theta y is the rotation about y axis. Of course, in this formulation we don't have the rotation about z axis as the degree of freedom. But when we solve problems, say for example, if you take submarine structure, so that the whole thing is curved, and you would model each panel using these flat elements. So the orientation of elements is going to be different. So we need, like we did for the truss and frame elements transformation from a local coordinate system to a global coordinate system. So when we do that transformation, we also introduce the rotation about z axis as an additional degree of freedom. So similarly, when I talk of because there are 4 nodes and each node has got 5 degrees of freedom. So when I look at the elemental degrees of freedom, so elemental DOFs, so these are going to be basically 20, and which are nothing but all the values of UV, U naught, V naught, W, theta x, and theta y at all the nodes. So if you look at, since this is a 4 noded element, so if you look at the interpolation, so we would write u naught as basically in terms of 4 shape functions. The logic I have already discussed earlier, so that concept is same. So we have ni into u naught ie. So this is the interpolation for u naught. Yeah, no, we are writing u naught in terms of interpolation function ni, which is a function of xi and eta, and u naught I is the degree no values of u at no node I. So similarly, V naught would be written as summation I going from 1 to 4 ni V naught I. And similarly, W will be written I going from 1 to 4 ni Wi. Theta x, similar, no, all the variables are interpolated exactly in the same manner. So using the same set of shape functions, ni theta x I e, and theta y would be written as summation I going from 1 to 4 ni theta y I e. So this is how you interpolate all the variables, and you already know the shape function. So I'm not writing n1, n2, n3, and 4, the interpolation function for a 4 noded isoparametric element in terms of natural coordinates xi and eta. You already know, so I'm not writing that. And since it's isoparametric interpolation, we interpolate the x coordinates also, x and y coordinates, using the same interpolation function. So ni into xi, and y coordinate would be similarly I going from 1 to 4 ni yi. And the only difference is that xi and y are the known x and y coordinates of an ith node of the element. So this is the interpolation we are actually going to use. Now if we want to write the whole this interpolation into a, in terms of the interpolation matrix H and the vector of elemental degrees of freedom. So let me write that. So if we write u naught, v naught, w, theta x, and theta y, now we have these 5 unknown variables. So see, in 3D we had only 3 degrees of freedom, but in this plate bending element, but then that those 3 variables u v w were functions of x y z, all the 3 coordinates. So now we have converted that 3D problem into a 2D problem, but then we have now 5 unknowns which are all functions of only x and y. So z coordinate is eliminated. We have taken the linear variation of u and v along z. So that is why we have the 5 degrees of freedom no in this case. So these 5 unknown displacements are written in terms of the matrix involving shape functions and the vector of elemental degrees of freedom. So if you look at the vector of no elemental degrees of freedom, so let me first write those. So first all the degrees of freedom at the first node. So u naught 1 e, v naught 1 e, w1 e, theta x1 e, theta y1 e, like that you will have. And then for the second node, so u naught 2 e, v naught 2 e, and so on, like that you will have. And then finally for the last node you will have u naught 4e, v naught 4e, w4e, theta x4e, and theta y4e. So these are the degrees of freedom. Now how do we write here this interpolation matrix in between? So we have already said that u naught is n1 u naught 1 plus n2 into u naught 2 plus n3 into u naught 3 and so on. So u naught is coming at in the vector of elemental degrees of freedom at location 1, then at location 6 and so on. So those locations we'll have to put the shape functions, and remaining places we put 0. So we will have n1 here, and then 0 0 0, then again n2 0 0 0, and then again n3 0 0 0, and so on. No, like that you have to do for this matrix. You have to you complete all the 20 columns. So it will have 20 columns. Then v naught is n1 v1 plus n2 v2 plus n3 v3, and v is coming at second location, at seventh location, and so on. So you put basically 0 here, n1 0 0 0, n2 0 0 0, n3 0 0, and so on. No, you need to complete that. Similarly, w is coming at the third location, and no, like that you can count. So it would be 0 0 n1, and then you have 0 0 n2, 0 0 0 0 n3, 0 0, and like that. And then the theta x is coming in the fourth location, and ninth location, and so on. So fourth location will put 0 0 n1, 0 0 n2, 0 0 0 n3, 0. And then theta y is coming at fifth location, 10th location. So we put n1 0 0 0 n2, 0 0 0 n3, and so on. So like that, no, you can complete this interpolation matrix H. So as you see, we can write this as H into DE. So H is interpolation matrix, and D is the vector of elemental degrees of freedom. So this is your H, and DE is the vector of elemental degrees of freedom. So this is your DE. So you would see that the formulation is more or less the same. Only thing is number of unknowns are more. So you can formulate a 4-noded plate bending element, you can formulate 8-noded plate bending element, you can formulate a 9-noded plate bending element, and so on in the same logic. So far whatever interpolation we have been discussing, so you could actually use the same logic to formulate this element. Because explicitly we have W separately in the total potential energy functional, as you have seen. So if you see the total potential energy functional over here, so because of this term we have separately W. So let me also write use a notation for the W interpolation also. So let me write separately also for W. So W can be written as it is involving the W1 W2 W3, which is at third location, eighth location, and so on. So we will have n1 0 0, and then again 0 0 n2, 0 0, and then again 0 0 n3, and so on. Into you will have this DE, same vector D which we have defined. So let me call this as interpolation for W as HW into DE. if you look at the sizes of these matrices, various matrices and vectors which are involved. So this is 5 by 1, and HU is, you would see this is 5 by actually 20, and D is 20 by 1. So same thing here. This is basically HW, which is 1 by 20, and this is 20 by 1, so that we get a single number. So another important quantity is your strain epsilon bar. So if you look at the epsilon bar, so epsilon bar we have said, no, if you look at the definition of epsilon bar, which was 8 by 1 vector, so we are going to write that. So yeah, let me slightly. So this is, we are going to write a epsilon bar again, basically in terms of the interpolation matrix. So now the degrees of freedom are the same. So we have this U naught 1 E, V naught 1 E, W1 E, theta x 1 E, theta y 1 E, U naught 2 E, V naught 2 E, W2E, and so on. No, you will have, and finally, no, for the last, you will have theta y 4E. So this is D or D. Now, if you look at epsilon bar, the first element was del U naught by del X. The second was del V naught by del Y. The third was del U naught by del Y plus del V naught by del X. And then the fourth was, those are curvature terms. So the curvature terms were, this was del theta y by del x, and then we had minus del theta x by del y, and then we had del theta y by del y minus del theta x by del x, and then we had theta y plus del w by del x, and theta x minus theta x plus del w by del y. So these are the elements of epsilon bar matrix, which is 8 by 1, we have already defined. Now we want to write del u naught by del x. So we know that u naught is n1 u naught 1 plus n2 u naught 2 plus n3 u naught 3 plus n4 u naught 4. So in those locations we have to put now its derivative with respect to x. So we put the derivative of say function, basically say functions n1 n2 n3 etc. with respect to no x. So we put here del n1 by del x, and then we will have 4 zeros, then we will have del n2 by del x, and 4 zeros, del n3 by del x, and 4 zeros, del n4 by del x, and 4 zeros. So that's the first term. So I will not write all the elements. Similarly you can complete this. So similarly del v naught by del y would involve v naught values at the node point. So we will have 0, and then we will have del n1 by del y 0 0 0 0, del n2 by del y, and so on. You can complete this matrix. And then del u naught by del y plus del v naught by del x. So the derivatives of both x and y are there. So we have here del n1 by del y, yeah. So we have del n1 by del y, because derivative of u naught is with respect to y and derivative of v naught is with respect to x. So we will have del n1 by del x, and then 3 0 0, and similarly del n2 by del y and del n2 by del x, and then we will have 0 0 0, and so on. So now next is del theta y by del x, and theta y is coming at the 5th 10th 15th and 20th locations, like that. So you will put at those locations, so 0 0 0 0, and then here derivative with respect to x. So del n1 del n1 by del x. Again 4 zeros, del n2 by del x, and like that. Now you will continue it. Then next is minus del theta x by del y, and theta x is at locations 4, 8, 12, etc., but with a minus sign, and derivative is with respect to y. So we will have 0, 0, 0 minus del n1 by del y, and then again 0, 0, 0, and yeah, one more 0, and then minus del n2 by del y, 0, and so on. So this is the interpolation of minus del theta x by del y. And then if you look at this term, del theta y by del y minus del theta x by del x, so this is involving both theta x and theta y, so which are no fourth and fifth variables in the vector of elemental degrees of freedom. So we will have 0, 0, 0, and then the derivative of theta x is with respect to x, so minus, we will have del n1 by del x, and theta y derivative is with respect to y, so del n1 by del y, and then 0, 0, 0, and then we will have minus del n2 by del x, and then del n2 by del y, and so on. Then if you look at the this one, the gamma xz, which is theta y plus del w by del x. So both no, in this w and theta y are involved. W is third, sixth degrees of freedom, like that. So we will have 0, and here we will have del n1 by del x. So because w is coming as derivative, del w by del x, and theta y is coming as it is, so we will have n1 here, and then again 0, 0, we will have del n2 by del x, and 0, and then n2, and then we will continue so on. Last one is minus theta x plus del w by del y. So w derivative is with respect to y, so we will have del n1 by del y, and then theta is coming as minus theta x, no derivative, so we put minus n1 here, 0, and then again 0, 0, del n2 by del y, and minus n2, 0, and so on. So this is how you would complete this B matrix, the entire B matrix. You can write it like this. So finally you would see that we can write this matrix epsilon bar as this matrix we are calling as B, and into this is vector of elemental degree of freedom. So this is your B, and this is your DE. So that you already know. So now once we have defined all the interpolations, so now we are ready to substitute these interpolations in the integral functional and develop the element level governing equations. So now the steps to develop the element level governing equations is same. So I'm not going into the detailed derivation of that, but I'm going to directly write the element level governing equation. So if you look at the element level governing equations, so now what you are going to do is what we have got, the interpolation for u naught v naught w theta x theta y equal to h into d, epsilon bar as b into d, and w as hw into d. So all these you substitute in the integral functional I, then take delta I and equate it to 0. So delta I equal to 0, and for arbitrary delta d gives you the element level governing equation. So that is what we get finally, the element level governing equation as Ke. The form of these equations is always the same. Ked is equal to F external for the element plus F internal. So now here what you do is now let me define the various matrices first. So now the Ke, and now instead of carrying out the integration with respect to xy, we convert this, because all the SA functions are written in terms of natural coordinates xi and eta, and similarly the B matrix is written in terms of natural coordinates xi and eta. So yeah, we put the integral in terms of with respect to integrations with respect to xi and eta. So then integration in xy would be equal to integration -1 to +1, integration -1 to +1, and the stiffness matrix you're going to have B transpose, then C bar matrix. It is not C but C bar. So you keep in mind that C bar is 8 by 8 matrix into again B, and then we have determinant J, D is high, D eta. So if you look at the C matrix, we have already said it is 8 by 8, and B is 8 by 20, and B transpose would be 20 by 8. So finally you would see the stiffness matrix is going to be of size 20 by 20. The stiffness matrix size is going to be 20 by 20 for this plate bending 8 noded 4 noded this isoparametric plate bending element. And as usual, we don't do this integration explicitly, but we carry out this integration through the Gauss quadrature numerical integration, which I have discussed earlier. So this is a 2D integral, so we write it as a double summation I going from 1 to n and j going from 1 to no, I use m and n, so let me just reverse this, although no one can use the other way around also. So integration I going from 1 to m, j going from 1 to n, and then this whole no, the B transpose into C bar into B into determinant of Jacobian matrix. Whole thing is evaluated at xi I eta j into wi wj. Wi wj are the weight factors. So we have already discussed how to get this these weight factors. And that is your Ke. Now if you look at the F external, which is coming only because of the distributed force along the z direction, force per unit area acting on the plate. So that again would be integration -1 to +1 -1 to +1. This involves only W, so we will have HW transpose, and then we will have Q determinant of J matrix into D high D eta. And this can also be written as a basically using Gauss quadrature can be converted into a summation. So I going from 1 to n dash, and j going from 1 m dash and n. I think I don't know why I'm every time. So this is m dash and this is n dash. You can write the other way also, but it doesn't. I am following this sequence. So we have HW transpose Q into determinant of J evaluated at xi I eta j into wi wj. So this is what your F external is going to be. And finally, the internal load is a boundary involving boundary integral. So that would be integration along the boundary of the element, and then we will have total this H transpose, and then the boundary forces. So there are forces and moments nnx, nny, and then we have Vz, mnx, and mny, and then ds. So this is your F internal. Now if you, so this is what now we have the element level governing equation for the plate bending element. So ultimately when you solve problems, so first you get the element level matrices, then you have to assemble, impose the boundary condition, and solve the problem. So that is how the whole thing goes here, and in this plate bending element formulation. Of course we also need to worry about number of Gauss points. So how do we decide that? So now, as I say, if we want to find out what should be m and n, so now this m and n, no, this is in going with B transpose C bar into B determinant J. So now if you look at this, let's say the element in the physical coordinate space, that is in the xy coordinate space, it is a rectangle. If it is a rectangle, then the Jacobian matrix is going to be constant, its determinant is going to be constant, and you can argue out that V will be linear in xi and eta. So when you multiply B transpose C bar into B into J, the whole thing would be quadratic in xi and quadratic in eta. So when we choose the number of Gauss points, so highest power is 2, so 2 plus 1 by 2 approximated to next integer, so it would be 2. So actually we'll have n is equal to m is equal to 2. Now if you look at the n dash and m dash, so if you look at again for the same rectangular element in the physical coordinate space, although actually element can be any arbitrary quadrilateral, but since we have 1 point, no, the n and m are coming out as 1.5 and we are using 2, so even it can handle slightly no non-quadrilateral rectangular elements, because then the main problem will come is because j would be functions of xi and eta. So the whole multiplication b transpose c bar bj would be higher than xi square and eta square, so you need a slightly higher gas no, number of points. But for a slight non-rectangularity, you can actually work with this energy n and m equal to 2. And now coming to m dash and n dash, so highest power of xi neta in hw, because this is a 4 noded element. So 4 noded elements means highest power of xi neta in the shape function is 1. So it for rectangular element it is going to remain same. So that means 1 plus 1 by 2, that is actually 1. So we could use n dash is equal to m dash is equal to 1, but there is no harm even if you use this equal to 2, because I know we use the points more than the minimum number of points required, it always leads to the exact integral. So there is no problem in using more number of points. Now one more problem which is associated with these shear deformable plate bending elements is known
Excuse me,
as,
sir.
yeah, yes please.
Sir, how did we decide n dash and m dash? And can you please give one example of this integration which we are doing using this
Yeah,
Gauss quadrature?
yeah,
And
so
will we?
yeah, Gauss quadrature numerical integration examples I have given earlier. So if you remember, I had talked about how the 1D integral is done numerically using Gauss quadrature numerical integration, then 2D integral, and if we have number of points, so how that physically transforms into summation of 4 terms and or summation of 2 terms depending on the 1D, 2D, and number of integration points. If you look back, we have already done those examples, but let me explain how I arrived at n dash is equal to m dash is equal to 1. So n dash and m dash are used for this integration. So what I am saying now, if you remember, I had discussed. So if no, the element is rectangle. If element is rectangle in xy space. So if you remember, we had done one example and we had said there that if this is the element, no, this is x and y, and this element is a rectangle, this is a and b. So then j, we had seen that j came out to be basically a by 2 0 0 and b by 2. So that means j is independent of basically the xi and eta coordinates. So similarly, J inverse, I had also discussed this, how we arrived at this whole thing. So that is 2 upon a 0, 0 and 2 upon b. So J inverse is also independent of xi and eta coordinate. Determinant of J in that case is going to be AB by 4, which is also independent of xi and eta coordinates. So now if you look at here HW HW is the interpolation of W, and that is in terms of N1, N2, N3, N4. And if you remember, for the 4 noded isoparametric elements, N1, N2, N3, N4 are linear in xi and eta. So the highest power of xi and eta in this HW matrix is going to be actually 1. And for a element rectangle in the physical coordinate space, xy coordinate space, this determinant j is constant. So then you see in the integrand, the quantity which we are integrating, in the integrand, the highest power of xi and eta is going to be 1. So we are deciding now, if I am writing say n dash, so the highest power of basically eta, so which is 1 plus 1 divided by 2, so that comes as 1. And similarly m dash is based on the highest power of xi, so highest power of xi is 1 in the integrand, so 1 plus 1 by 2 is equal to again 1. So that is how I said that no n dash is equal to m dash comes as unity. But you can use two, if you want to use the same integration rule, so that we can evaluate the basically the shape functions also at the same points where we are evaluating B matrix, so we don't have to recalculate it. So that is why we use the same points. So we actually, rather than using n dash m dash equal to 1, we use n dash m dash also equal to 2. So is that clear how we are arriving at n dash and m dash?
Yes, sir.
So no, I know if you go back, I had discussed, took some examples on Gauss quadrature numerical integration, and I had also sketched the locations of the Gauss point depending on the number of integration points and so on. So I think you should be able to bring back that concept which we are using over here. So now the next aspect in the plate bending elements is what is known as basically the shear locking. So if you remember, I have discussed that concept also in the uh, Timosenko beam element. So shear locking means if you use shear deformable. So shear deformable means in this particular element we have used first order shear deformation theory. So gamma xz and gamma yz and in turn tau xz and tau yz are non-zero. So if we have such a formulation, we call it as shear deformable plate bending element. And if we had no theta x and theta y written in terms of del w by del x and del w by del y, then then this plate theory is a classical plate theory, and then this shear locking does not arise over there because there is no shear deformation as such in that. So shear locking means when we use shear deformable. So let me also say here when shear deformable elements are used for modeling thin plates. Thin plates means let's say the A by H is greater than 20, basically more than 20. Then actually it would be more like, it would behave like a classical plate. I mean the normal would remain normal after deformation. So when shear deformable elements are used for modeling thin plates, the deflections no in this case W, the deflection is under predicted. So numerical this is a numerical problem. So this numerical problem is known as shear locking. So how do you eliminate, how to eliminate this? So then for what we do, this locking is coming because of the no the interpolation of no the integration and full integration and interpolation of transverse shear strains gamma xz and gamma yz, which are involving no the w the derivative of w with respect to x and y and theta x and theta y, which are coming as it is. So then one of the most popular technique is to eliminate this locking is known as reduced integration. So reduced integration is one of the technique to use eliminate the this shear locking. So then what you do is you use, and of course we use what is known as the selective reduced integration. So if you look at the KE we have split into this, we have written integration -1 to +1 -1 to +1 B transpose into C bar into B into determinant of J into d high d eta. So I know in this matrix is actually getting overestimated, and because of the shear locking, and the overestimation of stiffness would give lower deflection. So now how do we eliminate this? So then what we do is we split the total strain energy into two parts: the strain energy due to in plane strains, so that is epsilon xx, epsilon yy and gamma xy, and we separate out the strains, basically epsilon xz and epsilon yz. Those are transverse shear strains. So then this we split into two parts. We do integration -1 to +1, integration -1 to +1, and then let me use the interpolation for. Then what we do, what I am saying over here, that in this epsilon bar, you keep up to these 6 terms together, and the last 2 terms you'd separate them out. And so in the C bar matrix also it is 8 by 8 matrix. So we will take basically 6 by 6 no, along with the in plane strains, and last 2 by 2 rows and columns along with the transverse shear strains. So let us say the first 6 by 6 we take as no, this B bar, so B bar transpose, and then the 6 by 6 matrix out of 8 by 8 matrix, let me call it as ABD out of no, this C bar, and then we will have B bar, determinant of J, D is high D eta, and plus no, we split into -1 to +1, -1 to +1, and the remaining last 2 rows of B matrix I am calling as BS. So we will have BS transpose, and the last 2 rows and columns of C bar matrix I am calling as E, which is coming from the transverse shear strain. So you have this BS and the determinant of G D is high D eta. So where no B bar, as I said, it is going to be 6 by, now we are taking first 6 no, rows of B bar matrix. So this is 6 by 20, this is 20 by 6, and the first 6 rows and columns of 6 bar matrix, B C bar matrix, so this is 6 by 6. So overall it is still contributing to 20 by 20 matrix, but now the elements are less. And then BS is, we are taking last 2 rows of B bar, so that would be 2 by 20, its transpose is 20 by 2, and we are taking last 2 rows and columns of C bar, so that is going to be 2 by 2, and we are calling that as E. So this part is coming from the transverse shear strains. Transverse shear strains. Yeah.
So can you please
Yes.
repeat this ABD matrix part, please?
So now I just said, if you look at the C bar matrix, so if you remember, the C bar we have defined as integration minus h by 2 to plus h by 2, and this was that Z matrix we had formulated into C into Z dz. So this is 8 by 8 matrix. So now this 8 by 8 matrix would have 8 rows and 8 columns. So out of that, what we are saying is that first 6 rows and columns you are calling as ABD. I'm just using a notation. There is a reason, of course, for using this notation ABD, but it is for you. You just take it as ABD first 6 by 6 matrix, and these all would be actually 0 here. So you will have 0 0 0 0. That's how it would be. This matrix would be when you look at this, and then the last 2 rows are I'm calling here. Last 2 rows and columns, this I am calling as E matrix. Here also you will have 0 0 0 0 0 0 0 0 0 0. So these elements are going to be 0. So that is this first 6 by first 6 rows and columns I am calling as ABD matrix. So out of this C bar matrix, which comes from this Z transpose C into Z, C is a constitutive matrix. The first 6 rows and columns I am calling as ABD, and last 2 rows and columns I am calling as E matrix. These would actually be all 0 because there is no coupling between the in plane and the transverse shear strains and stresses. So you have, so similarly from B matrix you can take first 6 rows, so that is B bar, and last 2 rows we are calling as BS. So this contribution is coming from the in plane strains, epsilon xx, epsilon yy, and gamma xy, and these two are coming from transverse shear strains, that is basically gamma xz and gamma yz. So now what we do when we do the numerical integration, when we are using this same element for the thin plate problems, we do the reduced integration for this. So we said the exact integration order is 2 by 2 integration. So the shear part is integrated using basically 2 elements. So then what we do, this Ke we write as the summation I going from 1 to 2 j going from 1 to 2, and then we have this b bar transpose into abd. So you have now this abd and b bar determinant of j, this whole thing evaluated at xi I comma eta j wi wj. So whatever is involving epsilon xx epsilon yy and gamma xy, we are integrating using full integration, but for the transverse shear part we use one point integration, so one less than what is required for the exact integration. So we will do I is equal to 1 to 1 and j equal to 1 to 1. So this will be only one integration point. So j equal to 1 to n, and then we have no
Sir,
this bs
excuse me, sir.
trans. Yeah, yes, please. Yes.
Sir, can you please explain this I and J part, why we are taking 1 and 2?
I and j, why I am taking?
1 and 2. 2 for the first
So
part and
yeah,
1
so
for the second.
yeah, so what we are doing actually, because when this element is used for thin plate problems, so it leads to shear locking. That means if we use full integration, the stiffness is overestimated. So to correct for that, this shear part, that over stiffening is coming from the transverse shear part. So to reduce the stiffness, we are under integrating this transverse shear stiffness part. So this part, the second part here is coming from the transverse shear strain. So we also call it as the transverse shear stiffness. So this gets overestimated if we use full integration, and overestimated stiffness would under predict the deflection. So you will get the lower deflection. So to correct that, we are using the lesser number of gas points. So we will use, in this case, for the full integration you require 2 by 2 integration. So we use basically I equal to 1 and j equal to 1, bs transpose into E into bs into determinant of j, and this whole thing evaluated at xi I eta j wi wj. So that this one is, we call it as basically this one is reduced integration. So if you see, this is a full integration. Full means as per the actual requirement, and because we are using for the second part lesser number of points, so we call it as reduced integration to eliminate shear locking. So this reduced integration we are doing to eliminate the shear locking. So when we use this element for thin problems, we use the reduced integration for the transverse shear stiffness. It will predict the correct displacements. But if you use the full integration for the entire stiffness matrix, as I explained earlier, then it will give rise to locking. So no, it would predict lower deflections, what otherwise it would be. But of course, if you
Excuse
use
me,
it for
sir.
thin plate problems, then there is no problem.
Excuse me, sir.
Yeah, yes, please.
Sir, but in
Yes,
general, when we do this Gauss integration, we take I
yeah,
equal to 1 to 4. 1, we take I
not
equals to 1 to 4.
not
4
one to
points.
four. No. That depends on the problem.
So,
So it could
so
be, so
we are discussing about the plate, so 1 to 4, I guess, because we are
no,
discussing
no, no,
till now like
no, not 1 to. Who said 1 to 4?
because we are plating, we are doing on plates, sir.
So we have 1 to 4 in the sense I and j would be going 1 to 2. So if you remember, I have explained it. So I think you are confusing. So in the natural coordinate space, when you have two xi values and eta values, so let me explain you. I think you are, again, I have explained although that earlier, but here when I going from 1 to 2 and j equal to 1 to 2. So I equal to first one, j will take values 1 and 2. So xi 1 and along xi 1 you will have eta 1 and eta 2. So these are the 2 points, and then when you take I equal to 2, then zeta will again, j will take values 1 and 2. So we will get this. So these will be 4 integration points. So total there are 4 points, but I is taking for 4 noded isoparametric element. I will go from 1 to 2, j will go from 1 to 2. But the total number of points would be 4. because no, I have explained this. So I think this is xi 1 eta 1, this is xi 1 eta 2, and then this is xi 2 eta 1, and this is xi 2 eta 2. So these are, that is how the 4 points come. So it is not 1 to 4, and it depends on now if you use the say if you use 8 noded isoparametric element, then the interpolations would be involving xi square and eta square, and then you will use 2 plus 1 by 2, which is approximated to basically no you will get then you need to use say 2 highest power of xi and eta in the shape functions is 2, so it's when b transpose b you do xi power 4, so you will use 4 plus 1 by 2 approximated to next integer. So if you look at the 8 noded element, 8 noded isoparametric same plate bending element, 8 noded element, then the integration, no, your n m would be equal to actually 3. So 3 means then no, the total integration points are going to be 9. So it is not that I and j are going from 1 to 4. The integration points would be like this in the natural coordinate space for the 8 noded element. Is that clear? Your confusion that plate means two
Yes,
dimensional,
sir.
so 1D
Yes,
1D
sir.
means
Now it is clear.
2 points, so J means 1 to 4. No, it's not like that. It depends on the highest power of xi and eta in the integrand. So we see that highest power of xi and eta for the 4 noded element is 2. So we take 2 plus 1 by 2 approximated to next integer. So that is how 2 by 2 integration. But if the same thing, if we do 8 noded isoparametric element, then we will use n and m equal to 3. But now what we are doing here in the reduced integration, to eliminate the transverse shear locking, we are the transverse shear part we are under integrating, so that the stiffness is not overestimated, and that is the stiffness is correct, therefore stiffness is correctly estimated, and we get the correct stiffness and therefore the correct displacement for thin plate problems. Of course, when you are using this element for thick problems, then you use the full integration for the entire stiffness matrix. So yeah, I think I want to stop here, and the next class I want to cover no, there is in your syllabus there is a stability also. So I think the dynamics I won't be able to cover now, there is no time to discuss dynamics. So I will just introduce you to how to solve the stability problems, that is buckling problems, and then maybe no, I will also discuss some of the practical problems which are done using software. So I will share with you how they are modeled in the software, no, not showing you the software through slides. I will show you the problems and how they are discretized, modeled and solved, and then how the results are obtained. So that is what I would be doing in the next class. So I want to stop here. If you have any other questions and doubts, no, you can ask. Okay, so if there are no questions, I am stopping. Thank you all for your attention.